Continuing our Chapter 7 mechanism exploration, we are going to study hydroboration followed by oxidation. Oxidation. I don't know. Oxidation. Oxidation is the big one. Remember that was 6 steps? A lot of patterns we're supposed to look for. There's a 7th step on this one. It's called tautomerization. It's at the end. Same first 6 steps exactly as chapter 6. So you better be solid with that mechanism because it's our big one. When I say our big one, I mean for the whole semester. It's the biggest mechanism we got. And you know it's coming and you want to get all those points. So let's get ready. Hydroboration is the opposite. It's 2 arrows and you're done. 2 arrows. The number one mistake, though, happens right here. Students are so used to attacking H that they forget that H is now attached to a more electronegative B. Sorry, less electronegative B. I made the same mistake students make. I better write these electronegativities down. En. H. 2.1, that's a higher number than B. 2.0, that's why I'm attacking B. And you're going to get tired of being asked this question over and over. The electrons come back to which carbon? Say it loud, say it proud. More substituted? Yeah, we're going to go for the more substituted carbon. And there's, no intermediate. It goes straight and it's done. It's 1 step, both bonds give syn addition. Oh. If both bonds are done in 1 step, they will be on the same side. The H, more electronegative on the more substituted carbon. The B, less electronegative on the less substituted carbon. That's Markovnikov regioselectivity. They both got delivered to the same side. That's syn, stereoselectivity. I'm sorry, is what? The red? Which arrow? These 2 arrows? From pi right to the B, and from the middle of the sigma to the carbon. There's a carbon at the end of this arrow. She was asking where this thing ends. And it's that carbon right there. And there's the bond from that 2nd arrow. Now, I'm just going to briefly remind you this discussion we had the other day. If you look at this molecule without the H, which you're perfectly allowed to, right? You say, hey, he said syn addition, right? Well, then how can the product be trans? That's why we use different words for nomenclature and mechanisms. When you said syn, it's the 2 new groups going on the same side. When one of the groups is H, that messes you up with nomenclature because we never describe an H in nomenclature, right? We describe groups. That's where the trans comes from there. The groups are on the opposite side of the pi, right? But they weren't delivered that way. It was an H delivered the same time as the B to the same side. We have a word for the process. The process, syn. Deliver 2 new groups on the same side. There you go. We use syn and anti for mechanisms. We use cis and trans for nomenclature. Do never mix those up again or else you're going to start thinking syn addition gives trans products. What? And then half the time syn addition gives cis products. What? It's not making sense because they're talking about different things. Okay. All right, so that is the end of hydroboration. Now it's time to start numbering our steps. The number 1 I'm putting here. because the first step and the sixth step are both what type of reaction? Acid base. So I put it near the strong base for a good reason, right? Put up, please. If I don't have a lone pair on there, you have to put a lone pair on there because you're going to use it to make a bond. And there you go. Acid base. You're making OOH. That's an oxidizing agent. I'm going to make it purple. The first two times you make O- in this mechanism, you do the same thing with it each time. What is this thing? Yes, attack boron. O- lone pair makes a bond to boron in step 2. I'm going to stop drawing that H. Psi is a new group for us, and we got peroxide on the O, on the B, sorry. It is O. Make sure you show the OO bond, and don't forget boron's charge. What is it when it has 4 bonds? What's boron's charge? With 4 bonds. No, that's boron with 3 bonds. We already had that boron. It's right here. -1, did you say? Review. B with 2 bonds. B with 3 bonds. B with 4 bonds. And it's a review, so set it off to the side. Hey, owns B owns blank electron. Here it owns 2, 3, 4. Because sharing 4 is like owning 2. Sharing 6 is like owning 3. Sharing 8 is like owning 4. So what's your FC? Up there, it owns 3 on the periodic table. So if you own less than the periodic table, +1. If you own the same as the periodic table, 0. If you own 1 more electron than the periodic table, -1. End of story. Okay. And now we don't have room for the mechanism. That's okay. We'll work it. Step 2 is there. Step 3 is a unique step. And it is the only rearrangement in this class that's not with the carbocation. Okay? It's a unique rearrangement. And there's a reason for it because O bonded to O is an unhappy camper. O bonded to O has lone pair repulsion. Carbon says, I want to be bonded to O more than B because, you know, I'm more electronegative. I win. And OH- is liberated. And there's much joy because we got rid of the lone pair repulsion. And what do you got? You got over here, you got this. And now the bond, the black bond is up to the purple O, still up there, which is still bonded down there to a B. There still has 2 sec isoamyl groups. That never changes. And B's back to 3 bonds, right? 3 bonds, no charge. But you forgot that you made an O-. This is the second time you made an O-. You have to do the same thing you did the first time when you made O-. What was it? Attack the B. Back to 4 bonds to B, right? You got your iso. You got your C double C. We'll tidy it up a little with the angles, make them look a little low. Make them them look a little nicer. O is bonded to a B with two Sias. And it's got a new OH. That's 4 bonds. What's B's formal charge? -1. I think I just have to move those notes a little. I can move that a little. And you know, I gotta extend it a little. There we go. Then move the whole thing. I just want to get this mechanism in. Now, if you're trying to remember 5, you should always remember 4 and 5 together. 4 puts one of the oxygens on the boron. 5 takes the other oxygen off the boron. You can remember that. That's easy to remember, right? 4 puts an oxygen on the boron. 5, the other oxygen comes off the boron. So you find the other oxygen, which is the one attached to carbon, and it takes its electrons and scampers off there. It's just like a trade. Purple O minus. B, Sia2 has a purple O bonded to H. Show me that bond. That the bond didn't come out too nice. There we go. Must show bonds between H and O because step 6, just like step 1, was what kind of reaction? Acid base. I got the both molecules that I need right there. And I added a clue that wasn't on yours. I snuck this in. On the test, I try to put this there when it's made. So there's a clue you don't have. You could write it in up there if you want. Yeah, that's the product of OH losing its protons. This one. Acid base, do it. And if you want a cute way of showing that you also made that sec isoamyl boron thing, you could go like that. Made 2 things. Made this thing and what I'm about to draw thing. Now that purple O has an H, and we call it an enol. What do enols like to do? They don't like being enols, so don't say that. They like doing this. And what label did I put over that equilibrium arrow on the last one? It's got a big fancy name. Yes, nicely said too. He said tautomerization perfectly. Not bad. That word's too big for Scrabble. Okay, and what oh, you need an acid-base conjugate pair. Last time we used a strong acid and a weak base. Can I remind you? We used sulfuric acid and its weak base, hydrogen sulfate. The base always does the same thing, grabs which H? The alcohol H. The arrows happen the same again. Sigma becomes pi. Old pi breaks and picks up a proton from the conjugate acid. So I'm going to need an acid-base conjugate pair. And remember, the strongest partner you have here is this guy right here, right? So it's the base. What's its conjugate acid? Because you need its partner as well. What's the conjugate acid of hydroxide? Water. Put water on the other side of the molecule, near the pi. And see if you can remember those arrows from the previous page. Talk about first, what does the base do? Always the same. What do bases always do? Grab what kind of species? Starts with a P. proton from the acid. And that's the OH, right? Isn't that the same as the previous page? And then the sigma becomes pi, same as previous page. Old pi breaks and picks up a proton from the conjugate acid, same as previous page. Previous acid loses its bond between H and whatever H was attached to, just like the previous page. Same mechanism. Sorry, you can't copy anymore, but base takes H, sigma becomes pi, pi breaks and picks up a proton. Base takes H, sigma becomes pi, and pi breaks and picks up a proton. Wow, it's the same. And this morning's video, I reminded them by the end of Chem 242, they're going to see tautomerization, no less. It'll be at least 20 more times by the end of Orgo 2. Tautomerization is ubiquitous in chemistry and biochemistry. Organic chemistry and biochemistry are the same thing. Sorry. Yeah. Boron, it became this species here. So that's what I was trying to show with the side arrow. This became that. And this became this. And then the tautomerization with those two guys there. So that was the 7th step. I don't ever call it step 7, just call it tautomerization. Big picture, need everything on your thing except for the notes. You don't need the yellow stuff. Everything else you need. And we'll take it from there. I'll stop the video though.